Okay, Unit 8. This is 8.2. We're going to focus in 8.2 on mass conversions and percent yield. Understanding the amount of moles produced in a reaction is always important, but we can't measure moles. We don't have a scale that measures moles, or the amounts of atoms or particles in a particular reaction. So we know from a previous unit that we can use molar mass to convert moles to grams. And we'll do that by using that unit cancellation method that we're probably familiar with. And we did this on our whiteboards today, and you guys were all pretty good with this. But just to review again, let's say we've got 15.3 grams of oxygen gas. So remember, that's O2. Set up your unit analysis method. For every 1 mole of oxygen, you've got 32 grams. And why do I 32? I've got 32 because of this guy right here, right? Because of the 2. So it's 16 times 2. That's where I get 32 from. So 15 divided by 32, that's a little bit less than 0.5, right? So I don't know, 0.498 or something like that, okay? So 0.498 moles of O2. A couple of things here. Remember, significant figures important. Also, when you're reporting your answer, don't forget your units and your labels. Tell me what it is you're making. So that's converting from moles to mass. Let's look at an actual problem now and see how this can actually get a little bit more difficult. Say we've got 18.3 grams of potassium. This is potassium, and we're going to add that to aqueous iron chloride. And I do tell you that it's excess iron chloride, so FeCl2. Okay, and that's aqueous. And then on the back end of the reaction, I'm asking how much solid iron will this reaction produce? Well, if you know your single replacement reactions, you're going to know that that and that are your two products, and that's being the solid. And then obviously we have to go ahead and balance this equation, so we do have 2 there, 2 there. Okay. Now, we used our BCA table to try and figure out exactly what's going on, our before change and after table to figure this out. But what is the issue here? The issue is that the initial number given to us is actually in grams, and that's not all that helpful to us. BCA tables need moles. So the first thing that we've got to do is go ahead and convert 18.3 grams into moles, okay, to get the before. We also know that we have excess iron chloride, and we have no potassium chloride and no iron to start out. So we have to do that conversion in order to get 18.3 grams into moles. All right, so remember, you should do that to the right of your BCA table. I don't have a ton of room, so I'm just going to do it right here. So 18.3 grams of K. We know that the molar mass of K is 39.1 or so grams per 1 mole. So you've got 18.3 divided by 39.1, and that's going to give you 0.468 moles. So that's the amount of potassium that you have before the reaction. So 0.468, and that's moles. Now the change. Okay, we know that as this reaction proceeds, we are going to eat up 0.468 moles. Here it is. 0.468 moles of the potassium. It's going to be all gone. So that goes right here. And remember, that's minus. We got to have the minus sign up there. Okay. We're also going to lose some iron chloride. But we need to know how much iron chloride it is that we're going to lose. And that's dependent upon the mole ratio between potassium and iron chloride. So let's go ahead and figure that out real quickly. We've got 0.468 moles of K over 1. And we know that the ratio between that and iron chloride is 2 to 1. So 2 moles of K for every 1 mole of iron chloride. Those go away. Awesome. So 0.468 divided by 2 is 0.234. So we're going to change 0.234 moles of the iron chloride. And then on the right side of the table, we're going to have our products here. Now, if we look at the coefficients, we see for every 1 mole of potassium, we're going to form 1 mole of potassium chloride. So that number is going to be the same as we had for potassium on the left side. Okay, and again, for every 2 moles of potassium, we'll have 1 mole of iron. Well, that's the same as when we did the conversion between potassium here and iron chloride, so we're actually going to add 0.234 moles of the iron. Okay. And then we've got our after. Okay, this is our last section right here, the after. So we've got 0 for that. We still have excess iron chloride, and we now have 0.468 moles of KCl, and we have 0.234 moles of iron. Okay. Now, this is the number that we are most concerned with when trying to figure out the amount of mass of solid iron that we produced. So we're going to do that next. 0.234 moles, 0.234 moles of Fe, okay, and we want to know obviously how much mass that is. So we need the molar mass of iron, 55.85 grams per 1 mole, and you'll see moles cancel out. I put it like that, so mole on top, mole on bottom, those two things cancel out. And our final mass here is about 13 grams, right? Okay, it's about 13 grams. We should do sig figs and say it's about 13.0 grams of iron. There we go. Okay. So that's using the mass conversions and the BCA tables to be able to figure out how much product we're producing in a particular reaction. We'll do that for our copper and silver nitrate lab that we're doing currently. One last thing with 8.2 is we can calculate something called the percent yield, and it's going to be like the final thing that you'll have to calculate for this particular lab is percent yield. So it's a pretty simple calculation. Really all it asks is, like how well did you do? How well did you actually recoup the amount of product that you produced? So let's say, for instance, we run a reaction, and we run the reaction in the previous slide, and we only recoup 15 grams of iron. Let's change this, though. Let me see, just a second. I need to make sure that my math is correct, because my numbers aren't coming out in my head. Divided by 2. All right, there. Yeah, so I gotta change this. Let's say we only recoup 10 grams, 10.0 grams of iron. What is the percent yield of our reaction that we ran? So percent yield is just a simple equation. It's the actual yield divided by what we call the theoretical yield. Theoretical means what should you get if you do everything exactly correctly, you don't lose any material. Okay. Well, our actual yield is 10.0. That's the number that I would have to give you on a test. That's the number that you'll find from the scale in the lab. The theoretical yield is the number mathematically that you can figure out. We did that on the previous slide. Okay, that was like 13.0 grams. Okay, so we divide those two, and then we take that final number. We want a percentage, so we multiply that by 100. All right, and then we just figure out what our percent yield is. And obviously, you want that number to be as close to 100 as possible. We're getting about 76.9% right here, 76.9%. So you really want that as close to 100 as possible. And when you get to an AP class or advanced chem class, some of your grade will actually be determined by how well you do with that actual and percent yield. So, all right, that's 8.2.